All right, and welcome back. It's time to add the last few bits to chapter 5 on the window functions in SQL. And what we are adding here is 3 more ranking functions or siblings to the ranking functions that we've already seen. It's the percent rank, the cumulative distribution, and the NTILE functions. And they are also crucially depending on the ordering of rows in a table. So again, we will assume that the target table that we are operating over is ordered by an ordering criterion, just as we've talked about when we had dense rank and row number and rank on the table. All right, so that is the A-induced ordering of rows here. And once we have that, it makes sense, for example, to talk about percent rank. The percent of other rows that rank lower than the current row. So looking at the first row here, there is no other row that ranks lower than this first row here. So our percent rank would be 0. If you're looking at the last row here, all of the other rows rank lower than our current row itself. So that would be 100% or 1, or in this case 8/8. All right, so this is the semantics of the percent rank. A ranking regarding of the current row regarding all other rows expressed in percent. All right. Related function would be the cumulative distribution function, the cumdist window function. All right. This would look at the current row and all other rows that have been lower ranked than the current row. So everything that has been seen in that order from the beginning until we've reached the current row. How many percent of rows have we seen so far? Okay, so it's 9 rows overall here, so that's why you see this ratio with 9 here. And when we look at the first row, well, we have seen exactly 1 of the 9 rows so far. And if we go down the table, we have seen 2 of the 9 rows. And this is the group of rows that are ranked equally. So we have seen 5 of the 9 rows when we are completed with this group. So this is the cumulative distribution function. Of course, we have seen all of the 9 rows when we've reached the last row in the ordering, and including the current row, that would make for 100% of rows that we've seen so far. Right. Okay, and then there is the NTILE function, a function that lets you look at the collection of rows inside a table at a very well-defined granularity. The granularity is actually defined by this parameter to the NTILE function. So group the rows into n tiles. In this case, it's 3 tiles, of course, based on their ordering. So the first third of rows would be in the first tile, and it would be assigned the 1 here. The last third of rows would be in the third tile and would be assigned an n-tile value of 3 here. All right, so this is partitioning of the rows in 3 tiles or segments, if you will, based on the ordering by A, of course. All right, so this can be very useful if you want to look at data at different granularities, at granularities that you can control by the parameter that you give here to the NTILE function. You see that percent rank and cumulative distribution are more ranking functions than numbering functions in this sense. They really rank rows that are agreeing on the ordering criterion in equal fashion. Okay, so let's quickly switch over to the editor here where I brought this query with me. So you see that I've used the nice ratios in the slide presentation of the query, but if you execute just this query, then you will see, of course, the floating point values that we expected. We can see the n tiles, the 3 tiles that have been assigned. Let's enlarge this a bit. The 3 tiles that have been assigned to the rows, to the 9 rows. In this case, all the tiles have equal size, NTILE tries to best of its job to assign rows to tiles or segments of equal size, if this is possible at all. All right, so cumulative distribution and the percent rank. Okay, nice. Actually, if you look a bit closer at all of this, then you will see that this percent rank, cumulative distribution, and NTILEs are actually syntactic sugar for things that we could have expressed already using window functions that we know, namely the counting, so aggregation as a window function, and the rank window function that we've already seen in the last video. So this is a hint at how these functions over given Windows W could be expressed equally well by these functions that we've already seen. So indeed, these are syntactic sure, but they are quite useful and powerful and convenient syntactic sugar, which will become clearer if you look at this query, in which I've set side by side the new window function that we were currently talking about and their expansion, their syntactic desugaring in a sense, if we only rely on functions that we've already seen so far. So for example, for the percent rank function, you can see that we are looking at the rows that we have seen so far, of course, in win order. This is the window that we are talking about. Okay, that's no surprise. It's ordered by A, and as you know, this is equivalent to range unbounded preceding between unbounded preceding and current row. This is all implicit in these parentheses here. So in this expression of percent rank, we are indeed looking at the rank of all the rows that we've seen so far and put that into relationship with all the rows that are indeed available in the table. Count star over empty parentheses would count all the rows. In fact, we are only looking at the rows before the current row. This is the semantic of percent ranks. That's why we are subtracting 1 here in this particular case, but this ratio is just the percent rank. Similar observations could be made for the cumulative distribution. What we have seen so far in relationship to what is available at all in the entire table. So that would be 9 in our table, of choice, our playground table of choice here. And the NTILE function would just count everything that we've seen so far from the beginning of the table. So how many rows have we seen since we started the scan of the table from the beginning? So that would be this. I'm sorry, the counting should be included in this. That was this value. And of course, we would distribute that in even fashion over, in this case, 3 tiles or 3 segments. So that's the division by 3 here. And that would just simulate the behavior of the NTILE function. All right, so indeed it appears these guys are just syntactic sugar. Let's check that. That's a rather wide output here, but well, maybe you can see that if you perform the query on your own terminals, which you then can easily widen in the output. Oh, let's do this here. Let's do this here. That's fine. Maybe this is sufficient already. No, not yet. All right. Now you can see that these indeed are computing the same thing. We are talking about syntactic sugar. All right. So increase font size again. Later on that will be crucial. Okay. Right. Okay. So what can you do with these functions? Well, a lot again. There are just in the same pot as the row number, dense rank, and rank functions regarding their utility in many problem scenarios. Let's switch over to the slides again and look at one very simple example of how we could use these functions in classifying the altitude in a mountain shape again. So this is a different mountain shape this time. You see there's the resolution is a bit higher than the mountain shape we were looking at right now, but the idea is the same. This is just an x coordinate, and a record of the altitude at this particular x-coordinate. So for example, this would be the maximum altitude here, all right, at this x-coordinate. Okay, so what we could try to do if we are into geography would be to divide this landscape into different vegetation zones, equal size vegetation zones, like these zones 1, 2, 3, 4 here. So the higher we get, the higher would be the zone number that we are assigning, and this would probably have some impact on the plant life that we can find in this particular zone. All right, so you can already sense that this will probably be a job for NTILE, to have equal sized zones that we are using to classify the altitudes, and of course the ordering criterion would be the altitude here. All right, so the altitude for x-coordinate defines into which of these equal sized zones that particular x-coordinate would fall. All right, we could also use the same query to classify parts of this land as the lowlands and the highlands. As you can tell from this particular example, I'm not into geography, but I would characterize the lowlands as being in the lowest 20% of the altitude and the highlands in the 60 to 80% of the altitude. Everything above this would be considered really mountainous or the peak range. Okay, so this should be easily doable with all of the window functions that we've just introduced. All of these rely on an ordering regarding the altitude. And that's what we see here. This would be one example of this query. So let's see, we would of course iterate over all the entries in our mountains. I've brought the sample mountains table with me. We can do that in the terminal in a minute. All right. Of course, we would have windows defined on these entries in the table. A window defined on the altitude this time, not on the x-coordinate or something. It would be a window defined on the altitude. Okay, so that range we would that mountain zone we would classify into 4 equal sized vegetation or altitude zones. This is what you see with the NTILE 4 here. Okay, so any entry in the mountains table would be classified as being a member of the 1, 2, 3, or 4 mountain zone regarding this NTILE field call. Okay, and then the classification into the highlands and the lowlands. Well, this would just look at the percent rank, regarding altitude, of course. If we are in the percent range between 60 and 80%, we would be in the highlands. Otherwise, we could be in the lowlands if we are in the lowest 20% of the altitude range. Otherwise, there is no particular classifier I want to attach, and I'm just assigning the minus sign here. Okay, so let's see how that could look like in the terminal. Excuse me. I brought the mountains here, again with the x and the altitude information, the x-coordinate and the altitude, the height information. Let's create a table and then fill it with real mountain data. You see that there is even negative altitudes. Maybe there are some lakes there or similar, very deep valleys below sea level. All right, so let's insert this 26 entries in the mountains table. Okay, and then we would just post the query that you've just seen on the slide. All right, so build windows or build orderings of based on the altitude of the rows. Look at the NTILE, look at the percent ranks. You see the logic from the slide here, and I could just evaluate that and see the classification of our mountainous landscape. There's some lowland and some highlands that we find there, of course, yeah. And well, there's also the classification into vegetation zones. So in the lowlands, we would be in the range of 1. In the highlands, we would be in the range of 3 to 4, I guess. I guess so. Yes, we are. Lower lens are in the range of 1 to 2. Okay, so yeah, so that would be a job of classification based on these window functions: percent rank, cumulative distribution, and NTILE. All right, so I think I brought one final example with me that's not related to mountains and maps, but it's related to functions and their approximation. Actually, it's about a time series, a recording of measurements f of t that I've recorded at different points in time. So at point t0 here, that would be my recording. That would be my f value. At time t1, that would be my f value. And as you can see, I've recorded quite the number of f values here. And my goal here is to have a more coarse representation of this time series. So inside well-defined frames of time or segments of time, this would be one such segment of time, I would be content with a linear approximation of the values that I've recorded. All right, so I could forget about all the detail here in the middle. I would be willing to get rid of that, because I'm convinced that a linear approximation between the minimum value in the first value in the segment, and forgive me my crooked line here, a linear approximation in the segment between the first and the last timestamp in the segment would work just as well. And that would be a more compact representation. All of the points inside the segment would just be approximated by this line here. All right. So the job for me would be to just segment the time series data, in this case into equal sized segments. And once I have these segments, I would look at the first and last timestamps in this particular segment, look at their function values that have been recorded for these, and from these just simply generate this equation for the line inside the segment. So there would be this base value and then this incline m that I would compute just simply from these f values and the timestamps, and that these b and m values, these very compact two values would be the representation of the entire time series in the range between t0 and t1, between these two time stamps. Okay, so that looks like a job for NTILE, a job for NTILE that really helps me to partition the time series into equal-sized segments. And once I have the segments, I would use the segment information to build frames in the data. And once I've built such a frame based on these segments, I could access the first and the last value in the frame really easily. And easily access the recordings that we've made there to compute the b and m values for my linear equation. Let's do that. Let's switch over here to the window functions file again. All right. So no such experiment without the base data that we need for that. So this would be my experiment table, in which I record the timestamp and also the f value, the recorded value that I've measured at this particular time. So prepare that table, and let's fill it with 100 measurements that I've made. Okay. And then just fill in all these measurements. Random values should be okay here. All right. Okay, 100 entries inserted. And that's quite the table. 100 rows. Okay, all the random values that I've recorded. Nice. Okay, so now about the linear approximation. I would try to divide this series of 100 values that I've recorded into 5 segments. So let's define that into 5 segments, and we'll then just simply start with an NTILE call over this experiments table. All right, and the segments here we have just set it to 5, so we will partition or segment the time series data that we've recorded here into 5 segments. Each entry here will be the member of one of the segments, of course, in the order of the time when we've recorded these measurements. All right. So this is all we have to do for the first step, for the segmentation. So let's see. Yeah, it's already the CT is already prepared to output this intermediate result. So let's do that. Let's do that. Okay. Ah, there you go. Okay, so still the 100 rows, but we now have the very first column, the tile column or the segment column here. And we see that the first 20 values will be in the first tile, and the second 20 values will be in the second tile, and so on. So for each of these tiles, for these segments, we will build a frame. Inside the frame, access the first and last value and function value, and compute the linear approximation. So let's do that in the second step, where we build the segments. All right. Well, in this case, we will again use window functions, but this time we will partition by tile. So each tile will be processed on its own. Okay, that makes sense. For each of the tiles, we want to access the first and the last values and so on. All right. So inside each of these partitions, we will again order by timestamp, so that we don't lose the timestamp order inside each of these partitions. All rows inside the partition will be members of the frame. So we have 5 partitions, there will be 5 frames built. Okay, so all rows between unbounded preceding and unbounded following, all of the rows inside the partition will be member of the frame. Okay, right. So if this is the case, then let's look at the first timestamp and the last timestamp inside the frame. These are the T0 and T1 values that you've seen on the slide before. Okay, and we will record them as such, as T0 and T1. For each segment, we'll have the segment borders, the timestamp segment borders recorded now. We will also look at the function value at this particular point in time. As you can see, well, we would just look at the TF value, at the first value inside the frame, and the recorded F value at the last value inside the recorded frame. So we can access timestamp and function values here using the first value and last value function. Okay, so that's actually all we need. That's all we need for the computation of the B and the M parameters of our lines. Now recall that for all of these, for all of the rows, for all of the 20 rows inside such a segment, the first value and the last value regarding timestamp and function value will be the same. All right. It's sufficient to record this once inside each tile or inside each segment. So I will just perform a distinct on operation here. Inside each segment, it's sufficient to record these first and last values once. That's all we need. Okay, so that would be the segments information. So let's have a look at that. Okay, so for the 5 segments, for the minimum and maximum timestamps, these are the timestamps and the functions values that we have recorded. Exactly what we need to now compute the B and the M parameters for our equations for the lines, for the linear approximation. Okay, and that's what we are trying to do in the final step. Let me reactivate this here and disable this. And this. Yeah, okay. So just iterate over the 5 segments. For each of the segments, just record the beginning and the start, time span, and then then perform compute the incline and just the left-hand function value, the left-hand side, the leftmost function value inside each time span will be just the base B for the line. Okay, and that's all there is to it. This would be the linear approximation, the segment-wise linear approximation of the time series data that we've produced earlier. Okay, I think this concludes the examples for window functions in chapter 5. All that's left to do is maybe show this slide, which provides a nice overview of all the window functions that we have met. So you will find all these window functions listed in this particular column. All right. As you can see, I try to provide some order here. So some of the window functions, in particular all the aggregates, count, min, max, sum, and so on, all the aggregates, they are indeed dependent on the frame, as are the positional access functions that talk about the first and the last and the nth value inside a frame. So of course these are dependent on frames. It's not like that for the position access function that worked relative to the current row. The frame is no issue here. It's just the partition that makes that plays a role here. And this is what I try to indicate with the scope column here at the beginning. All right. So that would be row access inside a partition, and inside a partition, completely independent of any framing, there would be the row numbering and ranking functions. These are the functions that we have talked about in the last 2 videos. And that's about it. That is the family of window functions in SQL. And they should go into your toolbox because they make for a really strong addition there. We will see that in the course when we enter the chapter on recursive functions, when all of our examples get more interesting, more intricate, and more deep. And you will see the window functions pop up here and there everywhere. They should be good friends for every SQL developer. Okay, so much for the really long chapter on window functions. I hope you could enjoy that. There is really cool stuff ahead in chapter 6 on recursive function. Everything will be different once we enter the world of recursion, because then we can compute any function whatsoever in SQL. All right, this will be really, really thrilling, I would say. I'm looking forward to talk with you through chapter 6. All right, I hope you will be around then. See you. Bye.